So, hello everyone, this is lecture 7 for the atomic physics. In the last lecture, we were studying about the Sommerfeld model, and I explained you that how Sommerfeld gave this expression and how he explained using the Kepler's law and the angular momentum and different orbits. He explained that how you are getting the doublets and the relativistic mass change. That's how he explained. But see, that was not the correct explanation. He was just introduced this thing, so it was means beneficial for the future development. That's why we consider it. So the energy term after including relativistic mass effect will be means now we know the energy term is simply this one multiply with this is minus 13.6 z square by n square. But see, after correction it will be this alpha square z square by n square n upon k minus 3 upon 4. So see, this alpha is nothing but fine structure coefficient and its value is 1 upon 137, which is very small. When it will be square, it will be very much small. So this is something like you know in the perturbation theory, means the correction in the quantum mechanics. So this will be very small, so it is simply this. So now that's how you explain the energy. But see, this model failed to explain the doublet existence. So that's why we just consider it as a development, not a very much explained or the true explanation. Now see, after this we just got a roadblock, means there was no future development. They can't see that how can they explain these things, means there are two lines and three lines and multiple lines, so how can they explain? So they just see things in the magnetic way, means the cell structure and how the electron is moving inside the atom and it is getting current and current giving magnetic moment. So that's how they start thinking that way. And orbital and spin magnetism, to understand cell structure further, they start looking into the magnetic properties associated with the atoms. For this purpose they explored following aspects. So what they explored in the magnetics: so first was the orbital magnetic moment. That is because of the electron moving around the nucleus in the orbit. So this is the orbital magnetic moment due to the orbital motion of the electron around the nuclei. Second was spin magnetic moment. That was because of the spin of electron. Now see, that doesn't mean spin means that electron is rotating on its axis. So that is just name given. It is something intrinsic property of electron that gives its magnetic moment. So that, and in general we just call it as electron spin. So there was this magnetic moment. Then third was interaction between this mu L and mu S. So that's how they start thinking, and they can have parallel, or me now they have mu L and mu S we have. So now they can have interaction to each other. They can be parallelly interact, they can be anti-parallelly interact, and this parallel anti-parallel interaction will give different energies, and that's what we need to get the different lines, means the different energies. So they can have parallel or anti-parallel orientation, both will have different energies. So now they explore these things. So first we will see the orbital magnetic moment. So what is this? See, this electron is rotating. Now when electron is rotating, this is charge, and if electron is rotate, charge is rotate, then it will give a current loop, a small current loop, and the small current loop act as a dipole magnet, and now magnet will give you magnetic moment. See, you know magnetic moment formula, that is current into area. So what is the current? Current is nothing but charge per unit time in the particular time. So charge is q t, and time is nothing but 2 pi by omega, and this charge is minus e. So this will be your current. Now when an electron is orbiting in an orbit around the nucleus, then it acts as a tiny current loop, as I told you, which is equivalent to magnetic dipole. Now the magnetic dipole moment will be, so what is the magnetic dipole moment? That is current into area. So current will be this, multiply area is pi r square if radius is r. So this will be your magnetic dipole moment. Now see, anything is rotating in the solar system or anywhere under the central force system. So we study in the classical mechanics, then angular momentum will remain constant. And what is the formula of angular momentum? That is L equal to m omega r square, or you can see mvr. In place of v you can write r omega. That will give you m omega r square. So from here you can find the value of omega, that is L upon mr square, and substitute here in this formula. So in an orbit, then its angular momentum will be conserved because it is orbiting in the under center force, as I told you. So just substitute the value of omega L over mr square, you will get this formula for the orbital magnetic moment, that is minus e by 2ml. This equation says that orbital angular momentum and orbital magnetic moments are opposite to each other. See, you can see here this minus sign. See, told you that the direction of magnetic moment will be opposite to L. Now see how it is opposite. See the angular momentum, if you see that it is simply, if any particle is rotating, just to turn your fingers in the direction of the rotating, and the thumb will give you the direction of angular momentum. But see, magnetic moment depend on the charge and the current direction. So because of the electron is negatively charged, so the current will be in the opposite direction, and that will give you the magnetic moment in the downward direction. So that's why you are getting the opposite directions of mu L and L. If it will be for the proton, then it will give you the same direction. So that's why they have the opposite direction. This equation says that the orbital angular momentum and I have the opposite direction to each other because of the negative charge carried by electron. Now see, this is the formula for the orbital magnetic moment, but in general we give the formula is minus GL E by 2mL. This GL called the Landry factor. Now see why we introduce this GL term. See, we want to get the similar formulas for all the magnetic moments, like for the orbital or the spin, and the third we get from the interaction. So we want to get the same formula. That's why we introduce this. That for the orbital magnetic moment, we know this will be 1 like this. For spin it can be some other number, and for the third can be some other number. So that's why we introduce this factor. So we can just substitute 1 here for this. So that's why we introduce this. Now see, we are dealing at the microscopic level, so it is the quantum mechanics will play a role. So we know that the magnetic or the angular momentum at the microscopic level will be quantized. Quantized means it won't be continuous, means all possible values of angular momentum will not be there, only some discrete values will be there. And we know the formula for L is from the quantum mechanics, that is h cut under root L plus 1. So this will be the values which can be attained by the particle or the electron. So see, this will be your formula. Now E h cut by 2m is nothing but, if you find the value, this is your Bohr magneton, and this is nothing but magnetic moment. Its units are of magnetic moment, that is ampere meter square. So this is a constant value, that's why we just use it directly, that is mu b, and we call it as Bohr magneton. So this is the unit we use in the atomic physics, and there is a nuclear magnetron, that is we use in the nuclear physics. So it will be mu b. So now L will be under root L plus 1 h cut, and this L is nothing but orbital quantum number. So this formula will reduce to GL mu b under root L plus 1, means magnitude will be this. Now GL is 1 for the orbital magnetic moment, so formula will be this. So these are the values of magnetic moment which can be achieved for the electron. Now see, first you need to understand what is commutator algebra in quantum mechanics. So see, if you find the commutator of two operators, then if they commute, then you know that all the eigen functions or the eigen states will be same, and you can measure them together. But if they don't commute, then you can't measure the both operators simultaneously. So see, Lx, Ly, Ly, Lz, Lz, Lx, they never commute. So what you know, that if you know the x, you can't find the y or z. You can only know only the particular component of the angular momentum, not both of them. But L square and z commute, means if it will be Lx, then L will commute with that, and it will also commute with the Lz. So only particular one component or the total angular momentum you can find together. So that's why we can just see that for Lz, if we find, then L will be quantized according to the Lz. So how it will be? See, we know the total magnetic moment. So if you wanna find to the z component of this, so that will be minus GL E by 2m Lz, because it is simply L. So for z component it will be Lz here. Now see, we know that this particular direction, the angular momentum is also quantized, that is according to the magnetic quantum number, that is Lz equal to ml h cut. From the quantum mechanics you know this. Now ml value is nothing but, if L is 1, then ml will be minus 1, 0 and 1. So that's how, if L is there, then Lz will also quantized according to this formula. So you will have h cut 0, 0 h cut and 1 h cut values Lz. Now see, if we know that this Lz is quantized, so we know that according to this, if we can find Lz, we can also find L. So L will also quantize according to the Lz. So how can we see that? So let's find that. So Lz, if this is your L and this is your Lz, then when we know that Lz is nothing but L cos theta. So this is quantized, and you know, if you know this theta, then you know that what is the value of this particular L. So this theta can vary because this L can quantized, means for different values. So Lz is nothing but L cos theta. From here we can see that cos theta is Lz by L, and Lz is nothing but ml h cut, and L is LL plus 1 h cut. So h cut will cancel out. Now you will see that this cos theta is also quantized, means for different ml you will get different cos theta or theta. So for L equal to 1, you will have ml as plus 1, 0 and minus 1. So let's find the all theta values. So cos theta will be 1 upon root 2, cos theta 0, cos theta 3 minus 1 upon root 2. So theta 1 will be cos inverse this, cos inverse this, cos inverse this. Now you have three different orientations of L. Now you can see that L is also fixed, means direction of L is fixed in the space time. Okay, so particularly it is also quantized. So it will be theta 1, theta 2 and theta 3 according to these values. So that's how you know, if you can find the Lz, then this L can also be find, because you can just find one direction only. That's why we just consider by default the Lz direction. Now see, this is called the space quantization. Okay, So it means L cannot have any arbitrary direction in the space, rather its direction with respect to z axis is quantized, and this is called the space quantization. So I hope you get the idea. Now see, if you have the different L direction, that doesn't mean that orbit will be changed. It is just orientation is changed. Means you have the same orbit here also, and here also, like this. So all orbits are same, but their orientation will be different, and you can find the probability also that which orientation will be there. So from the quantum mechanics, you know how you can write this. For L equal to 1, this ML is -1, this is C1, this is C2, this is C3 for F11. Now probability is simply for first one. If this is a normalized wave function, then it will be P1 will be for first one C1 square, C2 square, C3 square. So that's how you can find also the probability. You understand this in the quantum mechanics for different orientations. Now see, that was all. So here also mu L was E by 2mL. So take this L here, and now you will see that this value is constant, and we call that the gyromagnetic ratio of the electron in the orbital motion, and this value remains same. It is independent of details of motion in the orbit. Now see how this everything is helpful to us. Now see, we have that orbital magnetic moment, and we have the current loop. So this current loop will give the magnetic field inside the, means this is a magnetic dipole acting as a magnetic dipole, so it will have the current magnetic field. So this magnetic field in this direction. Now see, there will be spin due to this electron. So there will be spin magnetic moment. So this spin magnetic moment will interact with the magnetic field and will give you the energy levels or the potential energy, and it can be different levels. So that's how we get the different levels, and we can define the spectrum or the different lines. So you will be, you know already this formula. This is mu s dot bl. This will interact, spin will interact with the magnetic field, and that will give you the potential energy. So spin orbit interaction. So that's how we will develop the model. So that's all for today. We'll meet you in the next lecture. Thank you everyone.